Recording in progress. Good morning, everyone. I hope that you're having a good Friday. Today is Friday the 18th. We are going to be going over gases today. Like I said yesterday, and I embarrassingly screwed up on a technical front of class. Um, I am going to go ahead and PowerPoint. Why are you doing this to me? Um, I introduced gases yesterday. I talked about kind of the relationships within gases. And one of the things that I encourage you to do when it comes to our conversations about gases and pressure and how gases react and how they behave is to try to think about an instance where, I guess, basically where you're familiar with a gas. Um, and what I would do is try to think of like situations that you've been in, maybe like cooking or something like that. Um, One of the things that I always think about when it comes to gases and how they behave is I think about whenever I was in, let's see, junior high. Me and some of my friends we would get like soda cans. They were full soda cans and we'd shake them up a whole lot. And whenever we shook them up, we didn't know this at the time, but what was happening was pressure was accumulating inside of those, um, or inside of those cans. And I think it's this one. Um, and so we'd shake them up and then we'd heat them up. And so we'd see the pressure accumulate because more gas was being evolved inside there. And then we were heating it and adding energy to the situation. And then we'd shoot it with a BB gun. And whenever we did that, what would happen? Well, that soda can would like pop off and go wild. So I encourage you to try to think about situations that you're familiar with from your life, and try to apply them in our discussion and conversation of gases. Okay, so what I'm going to do is I'm going to jump ahead to, I think it's our fourth slide. The four different gas laws that we're going to be getting into today. Our gas laws define relationships between the pressure and volume and temperature, pressure and temperature, volume and amount of a gas. So these are the four different laws that we're going to be exploring. The first law is commonly known as Boyle's law. And Boyle's law, it describes the relationship between pressure and volume. Now, whenever we're talking about, a relationship between pressure and volume, what that means is that everything else is held constant. Um, so the everything else would be temperature is held constant. So think about this as, you have a balloon or something like that, and you depress the sides of it. What's going to happen to the volume? So if you increase the pressure by pressing down, well, the volume is going to decrease. So you're increasing pressure, volume goes down. Now, if you're heating that or cooling that system, well, that's another variable that you have to account for. And Boyle's law basically doesn't ask anything about that variable because Boyle's law does not take that into consideration. Boyle's law is simply looking at the relationship between pressure and volume when temperature is constant. So if you're playing along at home with this one, what do you think will happen to the pressure when we increase the volume at constant temperature? Okay, so we're increasing our volume, our pressure is going to decrease. If we decreased, yeah, exactly. Great job. So now I'm going to jump ahead. This right here is a vacuum chamber, and inside that vacuum chamber, we've got a handful of different marshmallows. If you decrease the pressure, so basically you create a vacuum and you suck all the air out of this chamber, the pressure is going to go down. So what's going to happen to the size of these balloons? Those balloons are going to blow up. They're going to get massive because your pressure has gone down. The volume of those balloons will blow up. Now, same thing. Let's say that rather than removing air, you put more air into this and you increased pressure. Well, if you increase pressure, then the volume of those marshmallows is going to go down. Now, if you're familiar with, or I always like to think about this right here as being similar to a what's the word that a cylinder. I mean, it is a cylinder in shape, but I like to think about it in terms of being like a cylinder in a car engine. And so this piston will go up and it will go down. When that piston goes down, because you have increased a weight, you have increased the pressure, your pressure has gone from 1 atmosphere to 2 atmospheres. What happens to the volume? The volume gets cut in half whenever you double the pressure. So what happens to the volume when we double the pressure? It is halved. Okay, so whenever you see a relationship like this, where two different things are basically set equal to one another, these two things, P and V, are going to be indirectly related. If pressure goes up, volume goes down. This is an important thing to understand because if I were to give you an equation that looked like this, A and B are related. A1, B1 equals A2, B2. I want you to know the answer to the question, how are A and B related? Well, the answer is they are indirectly related. If you increase the quantity of A, well, then the quantity of B is going to go down. Now, that's this right here. I don't want you to dwell on that, but what I am getting at is I want you to, if I show you an equation, I want you to say, oh, okay, well, these two things being on the same side and it's a multiplication problem, that's indicating that this is an indirect relationship. Landon, that's a great question, and that's exactly where we're going because we're going to be looking at other variables and their relationships. Now, in terms of like the structure or formatting where they would be directly related, well, that would look something like this. X1 over Y1 equals X2 over Y2. Now, I don't want to turn this into a algebra or a math class, um, but I do want you to kind of be able to recognize those relationships. This right here, indirect. This right here, directly. So x1 over y2 or x1 over y1 is equal to x2 over y2. X and y are directly related to one another. Okay. So what I think so we'll kind of keep a running tally on this list here because it populates every so often. Pressure and volume, boils, and indirectly. If you know that, that's going to help you out quite a bit. And what I would recommend is this would be the sort of thing that maybe you put onto your note card in preparation for your next exam, because that pulls that information very quickly. Our next law relates volume and temperature to one another. When volume and temperature change, everything else is held constant. We are primarily concerned with pressure, volume, temperature, and amount. So if I say Charles's law, where we are looking at a relationship between volume and temperature, what that means is that we don't care about pressure because that's held constant. We don't care about amount because that's held constant. And you might be thinking, well, what does that mean? Okay, so what that means is let's let's visualize an experiment. What we have is I'm going to go with a balloon. And think about these scenarios as initial. How about I'm going to learn to spell that. Initial, INITIAL. And then I'm going to go ahead and call it final. So at the start and at the end. Now, at my screen, I'm sorry, I have a, yeah, there we go. I don't know if you guys have the live captioning pop up on your screen. I think that you can toggle it and turn it off, but for me, it was blocking part of my writing. If there's ever any time where you can't see something on the screen, please let me know. Or if you think, hey, are you talking about something that we should be seeing? Please don't hesitate to ask. Okay, so give me a number in the chat if you're comfortable with the idea of, okay, starting point and end point. Okay. Okay. So we're going to start things out. We've got a balloon. And let's say that that balloon we fill to 1 liter. And whenever I say fill it, I mean I just like let's get a bike pump or something like that. Hook it up to the balloon, pump, pump, pump. Okay, cool. It's approximately 1 liter. Okay. Do I care about the identity of the gas that's in there? I don't. All I care about is, well, the volume. Now, the initial setting is that that volume has 1 liter of gas and it is, let's say, 74 degrees Fahrenheit, which I'm going to go ahead and approximate to about 23 degrees Celsius, which converting that into Kelvin, that's going to be 296 Kelvin. Okay, so this is our starting point. This is our initial situation. We filled the balloon and that's the temperature that we're in. Now let's say that we take this balloon and we go to a butcher. And I'm using a butcher as an example because at a butcher, typically they're going to have a walk-in fridge. A walk-in fridge or freezer, um, something that's basically at probably maybe 4 degrees Celsius. I don't know what that is Fahrenheit wise. It would be like 43, 44 degrees. That doesn't really matter. What matters is that this at 4 degrees Celsius, I'm going to take that balloon in there, and 4 degrees Celsius is about 277 Kelvin. Okay, so I've changed the temperature. My temperature, now does everyone understand my initial state and my final state? The final state is I've taken the balloon into the walk-in fridge or the walk-in freezer. Great. So the volume started out at 1 liter. I didn't poke a hole in that or anything. The um so the volume of the freezer, sorry everyone. Um the volume of that balloon has not changed. Or I have not done anything to change it. I haven't poked a hole in it. I haven't removed any of the air or anything like that. But whenever I take it into this cold room, the volume, because Charles's law kind of explains that volume and temperature are directly related. If if temperature does something, volume's going to do the same thing. And so what that means is the volume is going to go down. Now, a fair question then is, well, how much is it going to go down? And to answer that question, you plug this in. So V1, our initial volume, 1. Our temperature was 290, I think we were looking at 296. And I'm going to set that, actually, you know what I'm going to do? I'm going to rewrite this. So 1 over 296 is equal to X, my volume. I don't know my volume. I do know my temperature, and that's 277. So what I'm going to do is I'm going to plug this in. 1 times 277 divided by 296. And that's whenever I get X equals 0.94 liters. So my temperature caused the volume to decrease. Okay, so that's Charles's law. So to give an update, we've got Boyle's for the relationship between pressure and volume. This is indirectly. Volume and temperature, Charles's law. And this is a direct relationship. Just to give you guys a little bit of foreshadowing, these three are all direct relationships. Okay, so our next law is Gay-Lussac's law. Gay-Lussac's law investigates or kind of explains, and whenever I say law, it's important to remember that these were observations that people made and then a name was attributed to them. It's not like Gay-Lussac, I can't remember if that's two people or one person or what their names are. Um, it's not as if they said pressure is directly related to temperature. That's how it is. It's not what happened. Instead, it was like this observation was made, and here we go. I think that's the law that governs gases. Okay, Gay-Lussac's law, we've got P and T on opposite sides of the equation. We saw that previously right here. Volume and temperature, opposite sides of the equation. V equals constant times T. That means they're directly related. Then we look at it in terms of an initial and final state like this. So this is a direct relationship. Now let's look at this question. What do you think will happen to the pressure when we increase the temperature at constant volume? Okay, so pressure increase. So P goes up. What happens to the temperature? Well, they are directly related. One variable goes up, the other variable. Didier said it. You're absolutely right. The temperature will increase as well. But what about the amount of gas? Not relevant. What about the volume? Not relevant because that's held constant. Okay, so here what we have, and this is a little bit tough to wrap your mind around. How can the pressure change if the volume remains fixed? Man, it's kind of crazy to think about that. But a situation, oh, sorry. This sort of situation says our pressure is at a certain point and our temperature is at a certain point. But the volume, this container right here, will not change at all in terms of its volume. The pressure and temperature will change. If one goes up, the other goes up. If the temperature goes down, the pressure goes down. The volume does not change at all. Now, what we have is, or the way that I think is appropriate to look at this is, I'm going to make this or rewrite the, no, I won't. I'm going to go with Boyle's. This is indirect. This is Charles, direct. GL for Gay-Lussac, and that is direct. And our last law is Avogadro's principle, or Avogadro's law. And this says there's a relationship between volume of a gas and the N, or the amount of a gas. Now, the way that I always kind of visualize this and think about this, we're going to see on the next slide. But if you add more gas, will that more gas need more space? Yeah, definitely. So the question is, what do you think will happen to the volume when we decrease the amount of gas particles at constant pressure? Okay, so we've got P, V, N, T. What do we care about for this? We care about volume and amount. We don't care about pressure. We don't care about temperature. We care about volume and amount. When volume decreases, what's going to happen to the amount of gas? It will also decrease. We see that visualized here. And I'll come back to the equation in just a moment, but in order to get this balloon to go from this size to this size, when the temperature and the pressure does not change, which if you're thinking, well, how would I know if the pressure changed or anything like that? Has anyone ever heard of barometric pressure? Or has anyone you watch the weather.com or you have the weather app on your phone. Um, and anytime that you're looking at that weather app, if you want to get into some of the more technical details of it, you can learn about the barometric pressure. And that's the pressure that is currently in the atmosphere. Oh, I spilled. And so if this person right here, if the difference between these pictures is like 5 seconds or something like that, nothing really in the environment has changed other than time. And so to go from A to B, what happened was this person blew more air into that balloon. So the question is, what happens to the volume when we double the amount of gas at constant pressure? Well, is it halved? Nope. Does it not change? Nope. It doubles. You're absolutely right, DDA. So this is a direct relationship. Now I'm going to go back to this slide right here so that I can add my last item. The relationship between amount of gas and volume is Avogadro's. And that is a direct relationship. Now, I think that it might be helpful to come up with like an acronym or a mnemonic or something like that. For instance, I always would just go shorthand and I'd say PVBI, VTCD, PTGLD, VAAD. Do any of those things spell words? No, they don't. But it's easier for me personally to remember PVBI and understand that that means, okay, pressure, volume. Ooh, what is the B? Oh, that's one of the laws. That's Boyle's law. What is the I? Oh, well, that's indirect. Or it might be helpful for you to say, okay, well, I'm going to go with like, I'm always curious and interested in like memorizing things and learning things. And so the way that people's brains work is always pretty interesting to me because I remember sequences of things, and that's really helpful for me. So I would remember this list in a general sequence, and I would think about it as, okay, the first thing is indirect, everything else is direct. What was the first thing? Oh, pressure, PVB, done. Okay, pressure, volume, boils. That's indirect because I've remembered that that's the first thing on my list. So then Charles, G, L, and A, those are all direct relationships. These are just some thoughts and suggestions on maybe how to address and approach this information. I know that it's not trivial, and yeah, so I would just kind of be thoughtful about that. Okay, now moving on from those laws, we're going to now talk about ideal gases. And whenever you hear that ideal gases, and you might think to yourself, what does that mean, ideal gas? What is a non-ideal gas? Well, methane. So what I want you guys to, yes, non-ideal. I gotcha. Yeah. Um, when you think about an ideal gas, think about this as a gas that is behaving how you want it to. And what I mean by that is ideal gases are going to be what we discuss in this class. There are things known as non-ideal gases, and not, yeah. And that is when a gas basically behaves in a different way. Um, and what I mean by that is it's something that's a little bit less, it's less predictable. Ideal gases are going to be something that's a little bit easier to follow. Now, this is the part of the class where we get a little bit more math intensive. But the good thing is there's an equation. The most complicated equation that you have has a total of 5 variables. I will always give you one of them. And that is the ideal gas equation, which is PV equals nRT. I know that some people always like to say Puvnert. Not sure why. I mean, actually, I think it's just because then people are like, ooh, it's a word. I can say it. And then my response to that is, Puvnert is not a word. Just because you make the sound with the letters doesn't mean that it's a word. But at any rate, PV equals nRT. We know these variables. P is pressure. V is volume. N is amount or number of moles. And T is temperature. R is a constant, and that's a value that I will always give you. Now, we'll dissect each one of these in just a moment. But here's what I want you to take away from, or this is just kind of a review of our gas laws. So, for starters, I've got all of the results highlighted. What I want you to do, and what I think would be helpful, is if you saw this sort of table and thought, oh, I know that. Okay, well, my relationship between, or this equation right here, boils. My relationship right here, Charles. My relationship here, GL or Gay-Lussac. And then last but not least, I'm going to stop with the circling. Last but not least is Avogadro's, which, I mean, my first chemistry class was whenever I was let's see, how old was I? A junior in high school. And I remember my instructor, Ms. Street was her name. She was, I think she probably said, yeah, most people like to say avocados. And I was like, yeah, word. Most people should because most people like avocados. And if you don't, that's fine. I'm not going to draw a line on the sand or anything like that. But Avogadro's law, I always think of Avogadro's law. Now, the next thing that I think about is, well, here's our little kind of prepositions or proposals here. If temperature goes up for Charles's law, what's volume going to do? It's going to go up. For Gay-Lussac's, if temperature goes up, pressure goes up. If amount goes up, volume goes up for Avogadro's. Boyle's law is our only indirect relationship. Um, for your quiz that is today, if you can do these, if you can know these relationships and identify the gases, that's going to help you. That's a spoiler, but it's also like, yeah, just do that. Okay. Now, there's another law beyond those 4 gas laws, known as the combined gas law. One thing that is important and is common throughout all of our discussion of gas laws is our temperature is always going to be in kelvins. Now, I want to see a response in the chat, and it's worth a bonus point on the final. I gotta write this on my final bonus point. I don't know if anyone does this, but just a little aside. Here's my to-do list, and I have a habit of, if you look closely, 7/17. Um, that's yesterday, but I didn't complete everything on my to-do list. So now what I've done is I've scribbled out 7/17, and now I've written 7/18, 2025, which I don't know if that's good or bad for my ADHD or general functioning. But nevertheless, here we are. Okay, so this is for a bonus point on the final exam. I'm looking for a word that describes the Kelvin scale. And my question is, why do we use it? My hint is the word I'm looking for starts with an A. The Kelvin scale is a yes. Okay, good. Now I can put that on my to-do list of yes. It's an absolute scale. What that means is that, or actually follow up for potentially another bonus point. Can it be negative 50 Kelvin? No, it's absolute. Goes to zero and goes up. That's it. 0 Kelvin is like theoretical. That's what people who are physicists and chemists, they decide, you know what? Looking at a chemical reaction is boring. So what I want to do is I want to live at the interface of chemistry and physics, and I'll know that as physical chemistry. And I just think of like deep abstract thoughts about the universe. When matter so, yeah, well, potentially. I mean, I'm so ignorant on the subject of absolute zero that I don't even know how to respond to that prompt, Sparrow. Like when matter stops acting like matter. Maybe. Maybe maybe when something is brought to absolute zero, it turns into a unicorn. I don't know. I'm guessing not because I've never seen a unicorn. I don't think they're real. Does everyone get a bonus point or just the first person? No, everyone. So that's, I gotta add two. Has to be, yeah, I don't know. I feel like absolute zero is kind of similar to infinity. And this is the point where, again, we're a chemist and a physicist. They live at this unique interface, and then all of a sudden, a philosopher comes in. And now they're just thinking about like very abstract topics and thoughts, and they're somehow not having an existential crisis every day. I don't know. Um, and I like Landon, I follow you, but I don't know. At the same time, we can come up with a number. We can say, oh, well, 0 degrees or 0.0 Kelvin is negative 273 degrees Celsius. Why not negative 275? But this is where it's like, yeah, we can define it, but then there is some limitation. Um, Landon, no. The physics breakdown and things start acting in waves and eccentric. I don't know. You've thrown wave behavior into the conversation, and yeah, I don't want to sound like a doofus. Sparrow, yes, yes. And you could actually even take that to there's no negative 0.00000000000001. There's no negative that? No, there's not. Or no, let me rephrase that. Maybe observable? Because definable, I don't know. Um, at any rate, we're going to move on from there because not a physics class, not a philosophy class, not a I don't understand abstract things like that class. So what I want us to come back to is our combined gas law. We use the Kelvin scale. And when you think about this from a math perspective, let's take volume. Have you ever gotten here, this Diet Dr. Pepper can, 355 milliliters. Um, could I get negative 300 milliliters of Diet Dr. Pepper? No. That just sounds silly. And you're right, it is. I use that kind of as a counter to, well, you can't have a negative temperature, or you can't have a negative temperature in Kelvin, because it's almost like you're taking a observed reality versus like a defined reality, or where humans have defined this is what this is. So negative 200 degrees Celsius, well, that's what humans have come up with a way to measure that. Okay, now with that in mind, let's go ahead and do a practice problem with the combined gas law. Now, when you see an equation like this, think about this as initial and final. So here what we have is a question. A balloon filled with helium gas at a volume of 22.4 liters. Okay, so this is our initial. V sub 1 equals 22.4. At a pressure of 1 atmosphere. Or if you see that and say, oh, at 1 ATM, well, ATM is a unit for measuring pressure. And I want you to be familiar with that. There are other units. For instance, if you add air to the tires in your car or your bicycle, that's typically going to be in PSI or kPa or PA, pascals or kilopascals. The units that we use in this class are atmospheres. So our pressure is 1 ATM. And our temperature is 0 degrees Celsius. Okay, this presents a problem. And a clear reason why we've got to switch from 0 degrees Celsius to Kelvin. If we use 0 degrees Celsius, that would make this whole thing 0. And so then we'd say, okay, well, that does not exist. But that does absolutely exist. So we say this is 273 Kelvin. 273. Okay. Give me a number in the chat if you follow that. Okay, great. So well done, DDA. 1 atmosphere. I'm going to set this equation up. P is 1 atmosphere. I got that right there. Volume is 22.4. And then temperature is 273. Okay. Okay. I'm going to set that equal to something. So this is my initial, this is my starting point. And then what I'm going to do is I'm going to come up with an explanation for 2 different options. What is the volume of the balloon? So does that balloon grow or does it shrink when our pressure increases? Okay, so if we think about this where we're not combining gas laws, P and V, well, that would be Boyle's law. So if we were just looking at it, that's right, it's an indirect relationship. So if only the pressure went up, then the volume would go down. And this question is asking about volume. But we're not dealing with just the volume or just the pressure changing. Instead, we're looking at the temperature changing as well. So what we're going to do is we're going to say this on the left-hand side of this equation is equal to 2 times V sub 2. That's our volume. Over T sub 2. Okay, T sub 2 is our new temperature, our final temperature. DDA, thank you so much. 223. Now, where we go with that is we say, all right, well, on the left-hand side, what's 22.4 times 1? Well, that's 22.4. Then 22.4 divided by 273 equals 0.08205. I'm going to set that equal to 2 times V2 over 223. 2V2 over 223. So now I'll take 223 and I'll multiply it by that 0.08205. And this number right here that I just drew a squiggle number, I plugged it in my calculator. So now I'm going to say 0.08205 times 223. And I get 18.297 V2. Oh, oopsies, sorry. Got ahead of myself. Is equal to 2 V2. I'll divide this by 2. I'll divide that by 2. And then I'll get 9.14. Nice, DDA. 9.1485 is equal to V2. So what happened to my volume? Whenever my pressure went up and my temperature went down, it decreased. Is that a big surprise? Not really. It's not a big surprise because both of those things, the pressure going up and the temperature going down, should cause the volume to go down. Now, this next question, B, flips this a little bit. I'm going to erase all this work over here. In this case, we've got the pressure going up and the temperature going up. Well, the pressure going up should cause the volume to go down, but the temperature going up should cause the volume to go up. And so now our question is, well, what is our new temperature? What is our T2? Our T2 is 50 degrees Celsius or, nice, DDA, 323 Kelvin. Now, most everything else is the same, so I could have saved some of what I wrote, but I didn't. So I'm going to do 22.4 divided by 273. Again, that's the 0.08205. I'm going to set that equal to 2V2 over 323. I'm going to again multiply this 0.08205 by 323. So I've got 26.5, nice, is equal to 2V2. Divide each side by 2. And I get, dang, DDA, this is a good race. This is a good race. You beat me. 13.25. Okay, so what happened to our volume? From its initial point of 22.4, our volume went down. Did it go down as much? No. Here, answer option A is like 9.5, I'll say. And then B is 13.25. So you could look at that and say, well, what has a bigger impact? And this is just analysis. This isn't something where you're like, oh, I need to remember that. This is analyzing. Okay, what had a bigger impact on the volume? A change in temperature or the change in pressure? I'd look at this and I'd say, well, the change in pressure going from 1 to 2 atmospheres caused the pressure or caused the volume to go way down. Change in temperature, dropping 50 degrees, a 100-degree swing basically did offset the impact of the pressure change. Can I get a number in the chat if you follow that, or a letter if you're like, wait, what? So what we do is essentially look at these questions and we itemize out the initial and the final. Detail everything here. And then we've got a prompt here. And answer option A. says when our pressure goes up to 2 atmospheres and our temperature drops 50 degrees, both of those things contribute to the volume going down. So seeing the volume go from 22.4 to 9.5, not a big shocker. Because, I'm this isn't a question where I'd be like, what do you think it is? Do you think it's 10? Do you think it's 11? Do you think it's 13? What's the new volume? This is instead like, let's just look at this. Let's plug the numbers in, see where it gets us. Our volume goes from 22.4 to 9.5. Now, when we look at example B, again, we're starting with the same initial parameters. 22.4 is the volume. This question is asking us, well, what's the volume after our pressure goes up, which is the exact same as scenario A, and then our temperature, it goes from 0 to 50 degrees Celsius. So example A is the temperature goes 0 to -50, so temp drops 50. And example B is temp goes up 50. Now, both cases, the volume goes from 22.4 to a lower amount. Okay. Was answer option A surprising? No. We expected that it was going to go down. How much we didn't really know, but we knew that it was going to go down. Answer option B is where we're like, okay, well, the pressure going up is going to cause the volume to go down. I got that. But we're also increasing the temperature. Well, increasing the temperature should cause the volume to go up. But how much does it go up? That's the question that we're really getting at here. And that's the answer that we're really getting at here. This is almost a question of like, the way that I think about it is, or what I think is an appropriate way to think about this is scenario A. Let's say that you go into your kitchen this morning and you say, you know what? I want to participate in a bodybuilding competition. How am I going to do that? Well, I got to get down to 3% body fat. How am I going to do that? If I watch what I eat very precisely and I'm very careful with the macros that I take in, and I lift lots of weight, I have this very rigid exercise routine, I'm going to get to where I want to go. I'm going to get to that desired 3% body fat. And you do all the math and you're like, yes, this is the number of calories. This is how often I need to eat. These are the exercises that I'm going to do. I'm going to get there. That's scenario A. Scenario B is where you say, okay, well, let's see. I need my goal is to get to 3% body fat. And here's what I know. I can do all the working out. I can do all of that. My schedule accommodates that, no problem whatsoever. But I like ice cream. I really like ice cream. And you know what? I'm going to have an ice cream sandwich with every meal of the day. That's all there is to it. A versus B. A is, well, if you cut your calories and you add this exercise, you're going to get to that new point. Both of those things are going to contribute to you getting to this new physique. Option B is you're going to do the working out, but you're not going to really do any of the calories. And in fact, you might actually add more calories. So you might not improve what you're eating, or you might not, let me rephrase that. Rather than improve, you might not, your eating might not be as facilitating to you getting to that 3% body fat. The question is with B is, are you going to get close to where you want to go? Well, if you do lots of working out, if you do lots of it, if you do tons of it, you're going to make progress. but is it going to be as much progress as if you do the working out and the calorie cutting? I hope that analogy helps. Can you give me a letter in the chat if, yeah, okay, I follow that. Okay, great. Great. Um, so yeah, I just thought of that off the cuff. That's a good one. Good job, Joel. And most importantly, it helped y'all because yeah, there we go. Okay, so that's what's going on here with this equation, this work right here. Now that's what the combined gas law is, where you are changing two variables. We're changing here, we're looking at what is the volume after we change both the pressure and the temperature. Now, the ideal gas law or the ideal gas equation right here, PV equals nRT. R is going to be something that's always provided for you. Pressure is always going to be measured in atmospheres. If you were to see a problem that related to kilopascals or something like that, that can be converted, but that's not something that we're going to be doing in this class. R, I'm happy that you asked that, and I'm going to come back to that in just a second. B is volume, that's always going to be measured in liters. T is temperature, is always going to be measured in Kelvin, and N, I'm sorry, is always going to be the amount measured in moles. R is known as it doesn't really have a fantastic name, but ideal gas constant. So this is essentially a value that says, all right, well, you have an ideal gas and with all of these other parameters and this specific value, what can you learn? Now, what this gets to is a question like you see here. So here is an example of an ideal gas question. What volume is occupied by, I'm going to change to the highlighter, 0.5 moles of gas? And I'm going to highlight each one of these individual variables as we work through it. What is N? Well, in this equation, N is 0.5. 0.5 moles of a gas at 1 atmosphere. 1 atmosphere is what our pressure is. And 25 degrees Celsius. Okay, we've got a problem there. Our temperature should be measured in Kelvin, but 25 degrees Celsius, we can convert that to Kelvin by, well, simply writing 298 K. Now, so the question that's being asked is what volume? So V is the unknown. When you have an ideal gas equation or question like this, you'll be given this R value, 0.0821. And whenever you want to answer a question like this, all that you need to do is you need to isolate the variable that you're being asked about. So this equation, all that we're going to do is we're going to say V is equal to nRT over P. We've rearranged this equation. We've just done the simple algebra to say, okay, well, I want to know the value for V, volume. How do I do that? I leave it alone. I move other parts of the equation so that V is by itself. And you might think, okay, well, why? Well, the reason is because this number, this V, is a variable that we do not know the value of. But our equation, our question prompt gives us the value for N. That N is 0.5 moles. We also have the value for R. R is 0.0821. T, 298, because we added 273 to it. And then last but not least, P for pressure, which is, in this case, 1. So if I plug all that in, 0.5 times 0.0821 times 298, we get V is equal to 12.23 liters. Now, one thing that's super important about this is, what is the gas that we're talking about here? Tell me the identity of the gas. And whenever I say that, I mean, is it oxygen? Is it carbon dioxide? Is it methane? Look at this slide, and based on the information that's in this slide and the information that I've said, tell me in the chat what it is. You're right. You don't know. You shouldn't know. You don't need to know. The identity of the gas does not matter. So this problem says 0.5 moles of a gas. It doesn't matter if it's O2, if it's xenon, if it's methane, if it's propane. It does not matter, because that's not a part of this equation. Now, essentially, R is the ideal gas constant. If you're looking for, does it stand for like rutabaga? No, it doesn't. If whatever the R is for representing a word, I do not know what that is. I'm sure I would bet that it's possibly Latin in origin. I don't know though. YR, I don't know. Okay. So what I want you to know about, and what's important to take away from this, is to know, when do I use one of these equations or the other? The ideal gas law. This is when you are given information about the gas. When you use the ideal gas law, PV equals nRT, and again, R is always going to be provided for you. When the amount of the gas is provided. Now, the next item of importance is that P, or pressure, must be in atmospheres. The combined gas law says, well, use when the conditions change. Okay. Now, what I want to do is I want to run through 2 examples. I can give you some question stems. And there are 2 slides here. One is just sort of a summary of all the gas laws. There it is. We've kind of talked about those, or we have not kind of. We have talked about those. So I'll leave that as a good reference for you. You know, if you're thinking ahead about, oh, what am I going to put on my note card? This could be a good thing. Obviously, maybe don't have the complete description. You know, take that and summarize it for yourself. And then this question right here, that's kind of what we're going to talk about. So what I want you to do is I want you to say which equation you're going to use based on the scenario that's described, A or B. And what I want you to do is critically look at this question. So do not answer until I say, give me your answer. Give me a number if you follow that. Great. Okay. So here's our scenario. 13 moles of a gas is in a chamber with a volume of 4.7 liters at 9.2 ATM and 42 degrees Celsius. Okay. Now, given that scenario, I think it's pretty reasonable to say, oh, okay, well, you gave us the amount of the gas. So I'm inclined to go with A. I'm not asking for answers yet because I don't actually have a question. Got a scenario though. An amount of a gas is in a chamber with a volume of 4.7 liters at a pressure 9.2 atmospheres and a temperature 42 degrees Celsius. This chamber is moved inside to 14 degrees Celsius and a pressure of 1 atmosphere. What is the new volume? Thinking about this scenario, give me your response. Are we going to use the ideal gas law or the combined gas law? Okay. Now, I think it's pretty reasonable to arrive at the ideal gas law. But let's look at the end of this question. And actually, let's look at the end of the question. What is the new volume? Okay. New. What's the new volume? That sort of suggests, hey, there's been a change. And did this question give us a change? Yeah. This chamber is moved inside to 14 degrees Celsius and a pressure of 1 atmosphere. So what we have is a change of conditions. So for this prompt right here, we want to use the combined gas law. And the reason for that is, well, the amount of our gas doesn't change. It's fixed. This doesn't ask us anything about an unknown variable. Now, I think that it's helpful to kind of go through. R is a value that I am always going to give you. So let's go through this question. And I always like to kind of pick off each of the variables in the equation. That's another way that I approach it and say, which equations do I need? Which equation do I need? Okay, 13 moles of a gas. Okay, I have then N. Got it. Oh, wait. You know what? I also have R because that's something that I will give you in your, or I will provide that to you. Okay, so I'm going to scribble N and R out. 13 moles of gas is in a chamber with a volume of 4.7 liters. So V, I've got that. Pressure is 9.2 atmospheres. And temperature is 42 degrees Celsius. Wait a minute. I've crossed out all the things that I know. So, seemingly based on the ideal gas law, I know everything. So the ideal gas law equation isn't going to help me answer this question because in my STEM, I processed all of the variables in the ideal gas law equation. Now let's look at the combined gas law. 13 moles of a gas is in a chamber with a volume of 4.7 liters, so 4.7. And I don't know necessarily if I'm going to use this. I've also got N equals 13. So volume is 4.7, pressure is 9.2, and a temperature is, I'm going to up that from 42 degrees Celsius to, that would be 315 Kelvin. This chamber is moved inside to 14 degrees Celsius. Okay, so that means our temperature is 200 and, let's see, 77. Nope. How about math, right, Joel? 287 Kelvin. Okay, so our temperature dropped. And a pressure of 1 atmosphere. What is our new volume? Oh, wait. Okay. So out, 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 out. The combined gas law gives us a variable that we don't know. So that's why that's the one that we want to use. V2, we do not know what V2 is. And that's why we would use this equation. Does everyone follow that? Like, if you saw a question, what are some of the keys that you're looking for? And if you do, add a number to the chat. Okay. 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 Now, with that in mind, this question gave us n equals 13. Did we need it? Okay. We didn't. So we got that information, but we basically could have said a gas is in a chamber. Duh. Sounds good. Or a container, whatever you want to say. Sometimes it's easier to, like, I always try to use the term chamber because it's like, oh, that's very technical. I think it's also easiest just to drop that word and say like balloon. Because that's something that you can kind of visualize. Maybe you can't visualize a 5 liter balloon because that would be definitely bigger than my head. But maybe that's good. Um, okay. So whenever you see the question, critically look at the information that you're provided with. If you get amount data, you might need that, but you also might not. The question is this asking about a change or is it not? And this scenario, this chamber, this container is moved inside. Okay, so we went from one environment to another environment, and things changed in that new environment. So we've got to account for that accordingly. Okay, well, that's what I've got for today. I'm going to stop the share. Um, I'm going to have a pre-recorded lecture for you guys Monday, and then I'm going to jump on Zoom after I get back from my doctor's appointment. Um, so I will be back then. And any questions that you might have over the course of the weekend, please email me. Um, Again, like I said yesterday, if you want to change the modality in which you take your exam, going from online to in person or in person to online, email me. I had somebody contact me yesterday and I have not responded, but yeah, I'm going to make that change. Later today, you should see, or maybe not today, but hopefully before the end of Sunday, you'll see, okay, here are the folks who are taking the exam online. You will have a quiz that opens today and closes. You know what? Rather than have it close tonight, I'm going to give you a little bit more time. I'm going to say it closes tomorrow night at 11:59 p.m. But with respect to that quiz, the names of the gas laws and what are the relationships of the gas laws and kind of the, you know, basics of gas laws is your basics of gas laws and variables is what I think is going to be a really good thing. Sorry, let me rephrase that. What I know is very valuable for you guys for this quiz. Other than that, I don't have anything else to add. I hope that you guys enjoy your weekend. And if anything comes up, email me. Monday I'll be available after I get back from my doctor's appointment. And Monday I'm pretty flexible in terms of office hours. So I'm glad to meet with you in the afternoon if you'd like. So just let me know. Thanks, everyone. I'm going to stop my recording now.